Hello everyone, good evening. So welcome to the session 7 on work, energy and power. So what we are doing is we are looking at the applications of the work energy theorem, right? So we talked about the applications of the work energy theorem in kinematics related kind of systems, the pulley, objects, etc. Then we have started the spring. So we'll just try to complete the spring and then we'll get into the vertical circular motion. Application of the work energy theorem in the vertical circular motion. Okay. So we'll begin with one sample question. This is a very standard one. In the figure given, there is a block A which is released from rest. You can see this is the block A. We are releasing from rest. What will happen? The block will start going down when the spring is in the natural length. So here initially the spring is the natural length. What happens as the block A is going down? The rope will other side rope will start going upright, so the spring will get elongated. The spring is going to get what? Elongated. Okay, now look at what they're asking. For the block B of mass m to leave contact with the ground at some stage, means at some stage they're asking us what? If the block B has to leave contact with the ground, then what should be the minimum mass of the block A? So if the block B, which is having a mass m, has to leave the contact with the ground, think about it. I mean, why will it leave the contact with the ground? Why it will leave the contact with the ground? Because let us see, as the spring is getting elongated, right? Spring will start exerting a spring force. As the spring is getting elongated, spring will start exerting the spring force on the block B. Spring force will be upwards. So for the block B to leave the contact with the ground, the thing is what? Spring force, because spring force will keep increasing. As the elongation is increasing, spring force will keep increasing, right? Spring force should be able to balance the weight of the block. The weight of the block is what? Mg, right? When the spring force is able to balance, it will actually leave the contact when the spring force is more than the weight. But as a limiting condition, what we can put? The leaving from the floor that will arise when spring force acting on that block is equal to weight of the block. Okay, so this is the situation that will have to come for the block B to leave the contact with the ground. That will happen at some stage. Now if that has to happen, they are asking what should be the minimum mass of the block A. Now let us understand what is this block A role here. What is the block A role? As the block A is going down, it will be losing its potential energy. Potential energy means gravitational potential energy. But the spring potential energy will be increasing. Now initially we are releasing the block A from rest. So as the block A is going down, the spring is going to get elongated. Now we are looking for what? The minimum mass of the block A, so that the block B can leave the surface contact. Here the block A, right, as it is going down, it will create more and more elongation in the spring. Correct. So for any mass, let us say block A is having a mass of m dash. We are looking at the maximum elongation that be created by block A. What is the maximum elongation means? Remember, as the block A is going down, finally it might come to rest at some point. Finally the block A might come to rest again at some point. In that case, since it is coming to rest, it will not be able to go any further down. That is what will be the maximum elongation situation. Now the maximum elongation, right, between the point 1 and point 2, initially also kinetic energy of the block is 0, finally also kinetic energy will be 0. What is happening? The gravitational potential energy loss, let us say it is coming down by a value x. What is the loss of gravitational potential energy? mgx. That is resulting in the gain of spring potential energy. Whatever the loss of the gravitational potential energy for the mass block A, that is resulting in what? Spring potential energy for the spring, which means, so by the way, this is not m, this is what? M dash, because we are taking the mass of block A as what? M dash. That is what we need to find. So the gravitational potential energy loss for the block A will be equal to what? Gain in the spring potential energy. This condition will be giving us what? The maximum elongation created by the block A. This will give us what is the maximum elongation created by the block A, because the thing is, we are assuming initially the block A is at rest, finally also it is at rest, means that is the maximum elongation concept. So look at here, one x we can cancel. So from here we will get what is that x value? It will be what? 2m dash g by k. This is the maximum elongation that can be created by the block A. Now if we are looking to find out what is the least value or the minimum value of the A, so that the block B will leave the contact with the ground, for that, whatever this maximum elongation spring force, because beyond this the block A will not be able to go any further down, which means what? The spring force will not increase beyond that. Whatever the maximum elongation spring force, right? What will be the maximum elongation spring force? Means created by block A moving down should balance the weight of the block B. Then only the block B will be able to lose the contact with the ground. So look at this. What is the maximum elongation spring force? 2m dash into g. That should be able to balance. Balance means what? Balance the weight of the block B, that is mg. G will be cancelled. What is the m dash value? m by 2. So if the block of A, if it is having a mass which is equal to m by 2, then when the block A is reaching that maximum elongation stage, it will be able to just make the block B to leave the contact with the ground. But if the mass of the block A is more than this, means even before reaching that maximum elongation point, it will be able to make the other side block B to leave the contact with the ground. Okay, so what is the answer for this question? They're asking us what? What should be the minimum mass of the block A? What is the minimum mass of the block A? That m dash should be having a minimum value of what? M by 2. M dash should be having a minimum value of how much? M by 2. Then the block B will be able to leave the contact with the ground. Okay, so even this question, right, we can even have the question being given with particular numericals. Like they can say, if there is a block of mass 6 kg on this side, it has to be leaving the contact with the ground. Then on the other side, what is the minimum value for the mass of the block required? So what is the answer for this? It will be what? The minimum mass of the block that will be kept on the other side will be what? It will be m by 2. Okay guys, So now we'll get into the last segment of discussion about the springs. I think this part we may have discussed in the laws of motion also, but this is kind of useful for us even when we go to the oscillations chapter. The combination of springs. What do you mean by combination of springs? Like the way we generally talk about, I mean, in 10th standard physics also we would have learned, like if you have electrical resistors, we can keep them in series or we can keep them in parallel like that. So here also we'll talk about what arranging the springs. Combination means we are looking at what arranging the springs in a particular format. Either we'll have what the series combination or the parallel combination. So we talk about the series combination of the springs or the parallel combination of the springs. What do you mean by series combination of the springs? Like look at it. You have a spring. It will have a common point with another spring. Maybe there can be a third spring like this. Spring 1, spring 2, spring 3 like that. So here we'll have a common point. This arrangement is what we call as the series arrangement. What will be a parallel arrangement? The springs will be connected end to end. So you can see here, these are what, this is the parallel arrangement. Okay, series means you'll have one common point. Parallel means what do you see? They will be connected. This side also they will be connected, other side also they will be connected. This arrangement is called as what? Parallel arrangement. Now what we'll do is, when you have a combination of springs, right, generally the combination of springs can be replaced by one single spring. Whether you have a series combination or the parallel combination, right, that can be replaced by one single spring. This is what we will generally refer to as the equivalent spring. Means whatever the force that the combination is creating, right, whether it is a series combination or parallel combination, that can be replaced by one spring. That is what we call as what? Equivalent spring. So here we will see how do you find the spring constant of that equivalent spring. Generally we'll represent this by K equivalent, K subscript EQ. Okay, so we'll see how do you find the spring constant of the equivalent spring for a series combination or for a parallel combination. So we'll start with the series combination. Like I said, right, what is a series combination? We have spring 1. Okay, it is having a common point with, so this is a common point with spring 2. Maybe we can have the third one also. We can have a fourth one. Like, we can have whatever number that we would be liking to have. Okay, so this is a series combination. Let us say the spring constants for them are what? K1, K2, K3. Now, if you try to elongate this combination, entire combination by a value x. We are trying to elongate the combination by a value x. Just think about it, right? You hold the combination, you elongate it by x. Each and every spring will not elongate by x. Maybe the spring 1 will have some elongation, let us call it as x1. Inside spring 2 there will be some elongation, let us call it as what? X2. Inside spring 3 there will be some elongation, x3. The total elongation will be what? X1 plus x2 plus x3. Elongation in the spring 1, because we are like, these are connected like this, right? You elongate it by a value x, which means the elongation in the spring 1 plus elongation in the spring 2 plus elongation in the spring 3. When you add it, you will get the total elongation. But when you have a series combination of springs, right, we said there is a common point. You can see here the common point. Here there is a common point. The common point, left side you will have the force due to the spring 1. Right side you will have the force due to spring 2. These two forces try to balance. Otherwise what will happen? The common point will keep getting displaced. The common point will have to be equilibrium, right? Which means what? Because once you elongate the spring and leave it, do you see the common point moving anywhere? No, right? It will be in equilibrium. Means what? The left side there is a spring force 1, right side there is spring force 2. Similarly, look at this common point. Left side will have spring force 2, right side there will be spring force 3. So since the common points, since the common points should maintain, what do we call it as, equilibrium. Since the common point should maintain equilibrium, what must happen? Each and every spring should possess, okay, same restoring force. This is a very important point about the combination of the springs in series. If you have combination of, maybe we can have 4 springs in series, the restoring force in spring 1 will be equal to restoring force in spring 2. That will be equal to restoring force in spring 3. That will be equal to restoring force in spring 4, like that. Okay. Now look at the concept of equivalent. We want to replace the entire combination by one single spring. That is what we call as the equivalent spring. The spring constant is what? K equivalent. When you elongate this by a value x, right, the force that will be there in the equivalent spring, because the series combination is producing how much force? Each of them is having the same value of force, right? Let us call it as what? F. What is this F? The common force. Equivalent spring should produce the same force, right? That is the basic idea of the equivalent spring, right? Equivalent spring should produce the same force when you give this elongation x. So look at this. What is the relation we have? The spring force F will be equal to what? K equivalent into x. From here we will get x is equal to what? F by K equivalent. Now for the spring 1, spring force F is equal to what? K1 into the elongation in the spring 1 is what? X1. So from here we will get X1. What is it? F by K1. For the spring 2, we will get X2 is equal to what? F by K2. For the spring 3, we will get X3 is equal to what? F by K3. I think now you are able to understand what we are going to arrive at finally. We are getting X1 is equal to what? F by K1. X2 is equal to F by K2. X3 is equal to, because each of these spring 1, spring 2, spring 3, they all have the same force. Look at this relation. The total elongation x is equal to what? X1 plus X2 plus X3, right? Which means what? X value, we'll take it from the equivalent spring. F by K equivalent is equal to what? F by K1, that is X1. F by K2, that is X2. F by K3, that is X3. So you can see on both sides we can cancel F. If we cancel F means what do we have? Left hand side, what are we having? 1 by K equivalent. Left hand side, what do we have? 1 by K equivalent. So we'll just write down the final result. This is the formula for finding the effective spring constant or the equivalent spring constant. What is it? Left hand side we have 1 by K equivalent is equal to what? Right hand side 1 by K1 plus 1 by K2 plus 1 by K3. If you have more number of spring means this will go on. Like say we have 10 number of springs. What do we have? 1 by K1 plus 1 by K2 plus 1 by K3 plus 1 by K4, like that up to 1 by K10. So this is how we will be able to find out what is the equivalent spring constant of the combination of the springs in series. This is one way of arranging them. Okay. Now from here, right, we will also look at a special case, that is cutting of the springs. What do you mean by cutting of the springs? Let us say we have a spring. We cut this into 2 parts. We will get 2 springs. Okay. So let us say the original spring is having a constant K. What is the original spring constant? It is K. If you divide the spring into 2 equal parts, first we are beginning with what? Dividing the spring symmetrically. We are dividing it into what? 2 equal parts. They are identical, right? So let us say each of them is having a spring constant K dash K dash. Now one way we can see it is, look at this half, and this half, it is like what? Both of them are in series. You connect them, they are in series, right? Then you are getting the original spring. It's like what? You connect them in series means you get the original spring, right? What is the relation we have? Original spring constant is K. 1 by K equivalent is equal to what? 1 by K dash plus 1 by K dash. Because we are assuming like what? These two parts, when they put in series, that is giving us the original spring. So original spring constant we know K. So 1 by K is equal to what? 1 by K dash plus 1 by K dash. What is this? 2 by K dash. So from here if you rearrange, right, what do we have? K dash is equal to 2K. So these small springs, right, they will have higher spring constant. So the stiffness constant, if you look at a spring and keep cutting it, right, what you will be observing? The smaller parts will be having a higher stiffness constant. Means if you want to elongate them or compress them, it will be difficult. So smaller parts of the spring, right, that's why if you have a longer spring means it will be easy to compress or elongate. But if you have a small spring means, right, it will be very difficult to elongate, even difficult to compress it. Okay, now look at this. If you divide this into three equal parts, let us call it as what? Each of them is having K double dash, K double dash, K double dash. Now what we'll have? 1 by K is equal to 1 by K double dash. It is like a series of 3 plus 1 by K double dash plus 1 by K double dash. From here what we'll have? 3 by K double dash is equal to 1 by 3 means K double dash is equal to 3K. So if you cut the spring into 3 equal parts, each of them is having how much spring constant? 3 times K. Okay. Now the idea is, if you divide this into 10 number of equal parts, each of these small springs will have how much spring constant? 10K, right? If you generalize it, okay, so we say that we are dividing the spring into some n number of equal parts. N can be any general number. It may be 2, 3, 5, 10, it can be anything. Then each of these small springs, right, will have a spring constant which is equal to n times of K. Each of these small parts will have a spring constant, like you can see here. If you divide this into 2 equal parts means each of them is having what? 2K. K is the spring constant of our original spring. If you divide them into 3 equal parts, each of the parts is having how much spring constant? 3K. Like that, 10 parts you divide means each of them will have 10K. Generalizing, if you divide into n parts, then each of them will be having a spring constant which is equal to what? N into K. Okay, so this is about dividing the spring into equal parts. But obviously we will get a doubt. What if we are dividing the spring into unequal parts? Because yes, if you divide the spring into equal parts means we are able to see. But what if we are dividing the spring into unequal parts? So from here, right, based on our discussion about the cutting of the spring into 2 equal parts, look at this, we will see one interesting relation. The original spring, let us say length is L. The 2 equal parts, right, each of them will have how much spring constant? 2K, 2K. What about their length going to be L by 2, L by 2? See, the original spring constant K into its length will be equal to, what about this part? Spring constant is 2K. What about the length? What about this part? Spring constant 2K. Length is what? So when you're having a spring and you're cutting it into different parts, the spring constant value multiplied by the length of the spring. Spring constant value multiplied by the length of the spring will be equal for all the parts. Spring constant value multiplied by the length of the spring will be equal for all the parts. This result is what we are going to use when we are looking at a problem where we are dividing the spring into unequal parts. So remember, what is it? For a given spring, right, when you are trying to divide this in different parts, each of these parts the spring constant value multiplied by the length of the part, that will be equal. Not only that, it will be also equal to what? The constant of the original spring and the original spring length. So look at this, we are say dividing into three parts. Okay, so the lengths are L1, L2, L3. Okay, let's say the spring constants are K1, K2, K3. Now what will be the relation we'll have? The original spring constant is what? K into its length is capital L. That will be equal to what? The spring constant for the first part, K1 into L1. That will be equal to the K2 into L2. That will be equal to what? K3 into L3. Okay, so this is the relation we need to look at. Using the relation, right, we can find what is K1, what is K2, what is K3. So what is the relation? If you are dividing a spring into some parts, may be equal, may not be equal, then the spring constant value of the part multiplied by the length of the part will be equal in all the cases, and that will be equal to what? The spring constant of the original spring multiplied by its length. Okay, so this is the relation we need to use when we are trying to find the spring constant values of the parts which are unequal. We'll just look at a question now. Look at this one. A spring of constant K is divided into three parts. What is the ratio of the length? 1:2:3. Means, let's say we have original spring of constant K and length L. We are dividing this into three parts. Okay, so let us say the spring constants are what? K1, K2, K3. We need to find them. They're asking us what is the spring constant for each part. Means we have to find what is K1, what is K2, what is K3. Okay, so look at this. They are giving us the ratio of the length as what? 1:2:3. Which means, how do you find out the so let us say the length is L1, here it is L2, here it is L3. You know what is L1 going to be? L1 will be what? One part. What is the total number of parts? 1 plus 2 plus 3, 6. So 1/6 into capital L. Similarly, L2 will be what? 2/6 into capital L. Why it is coming? The ratio divided by total sum of the ratios into the total spring length. L3 will be equal to what? 3/6 into L. So we can write it like what? 1/3 into L. This we can write it like what? 1/2 into L. Okay, so this is about the L1, L2, L3 values. Now what is the result we have? The original spring constant K into its length will be equal to what? K1 into L1. But what is L1? 1/6 into L, right? So L will get cancelled. So what we have? K1 is equal to 6, will go that side, numerator, 6K. Second, again K into L is equal to what? K2 into L2. L2 will be what? 1/3 L. Here also L will get cancelled. 3 will go that side. Means K2 is equal to 3K. Now comes the third. K into L is equal to what? K3 into L3. But what is L3? 1/2 L. L will get cancelled. 2 will go to the numerator. So K3 is equal to what? 2K. So look at this. What is the result for the K1, K2 and K3? K1 is equal to what? 6K. K2 is equal to 3K and K3 is equal to what? 2K. So whenever we are having a spring that is divided into unequal parts, what is the spring constants? What is the procedure to find the spring constant? We will have to look at the spring constant value of the particular part multiplied by the length of the part. That product will be same for all these parts, and the value will be also equal to what? The value will be also equal to the spring constant of the original spring multiplied by the length of the original spring. Okay, so this result we have to remember. So this is about the, what is it? The series combination of the springs and dividing the spring into parts. We have seen, dividing the spring into equal parts and dividing the spring into unequal parts. Then we'll talk about the parallel combination. Parallel means what? Like I said, imagine we have two springs which are connected to the object like this. Okay. So spring of constant K1, another spring of constant K2. Let us say we give a elongation X. So we'll see that spring 1 also will be elongated by the same value X. Spring 2 also will be elongated. So as a result, we'll have F1, F2. What will be F1 value? K1 into X. F2 value is what? K2 into X. Remember, total force acting on the mass is how much now? Because look at this, mass will experience what? F1 and F2. Total force is what? Which is equal to K1x plus K2x. This is the total force. If we say that we are replacing it just with one spring, that is our equivalent spring. If you move the mass by a value x, right, the equivalent spring should produce the same force. What is the force produced by the equivalent spring? What is the force produced by the equivalent spring? The spring constant into elongation. Now what is the condition we are saying? If we are having a parallel combination, we are replacing everything by just one spring. The total force that is given there should be produced by the just this one equivalent spring we are taking, which means what? What is the relation? The force produced by the equivalent spring is equal to what? Total force produced by the parallel combination, which is K1x plus K2x. So in a parallel combination, what we see? Each of these springs in parallel, they will have the same elongation. Like you can see, spring 1 is having the elongation x, means spring 2 also will have the same elongation because they are connected parallel. So here you can see x will get cancelled on either side. What do we have? K equivalent is equal to K1 plus K2. This is we have 2. If you have 3 means K equivalent is equal to what? K1 plus K2 plus K3. If you have 4 means K equivalent is what? K1 plus K2 plus K3 plus K4. If you have like 10 means what? K equivalent is K1 plus K2 up to 10. Okay, so this is about the parallel combination of the springs. Now we'll just take a look at this question. This question is kind of adding both the series side as well as the parallel side area. Look at this. A spring of constant K is divided into 3 equal parts. Divided into 3 equal parts. And these parts are kept in parallel. What is the spring constant of the combination? So there are two things we are doing here. What is it? First, we have a spring. We are cutting this into 3 equal parts. Remember, already we have seen it, right? If you divide a spring into 3 equal parts, what will be the spring constant of each of these parts? 3K, right? We have seen the general result also. If you are having a spring, we cut this into n equal parts. Then each of these parts will have how much spring constant? N times of K. So here we are dividing into 3 equal parts, means it will be what? 3 times of K. Got it? Now these are the 3 parts. Part 1, part 2, part 3. Now we are not stopping here. What we are doing? We are now keeping this combination in parallel, like the way we do. Okay, so this is how we are probably connecting them in parallel. Each of them is having a spring constant how much? 3K. What is the overall K equivalent? Parallel means what? K equivalent is equal to what? K1 plus K2 plus K3, like that, right? Which means what? 3K plus 3K plus 3K. What is it? Totally, what is it? 9K will come. So if you cut this spring into 3 equal parts, each of these parts will have how much? 3K, 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 like that. Now we are not stopping there. We are taking these parts and then putting them in parallel. When you put them in parallel means what? Each of these parts is now parallel, right? So the overall equivalent is what? K1 plus K2 plus K3, like that. That is the parallel combination. So we'll get it. What is it? The final spring constant of the combination, right, will be what? 9K it will come. You have to confirm it, guys, whether you are able to get the same answer or not. Okay, so check it. You must be getting what? 9K you should be getting. Okay, so with this, right, we are going to wind up the spring part, and we'll go to the next part, which is the applications of the work energy theorem in case of the vertical circular motion. So this one we'll get the introductory part in today's session, and we'll try to cover this in the next session also. Okay, because it will be quite some extensive idea in terms of the coverage. We'll also have to solve some problems. Okay, because as I said, right, from the JEE point of view, both mains level as well as advanced level, this vertical circular motion example, right, is a very standard one. Okay, so what is the vertical circular motion? We talked about the circular motion. We have some idea. The particle will be in a what? In a motion where it will always maintain a constant distance from a fixed point. Well, how do you define a circular motion? You'll have a fixed point. The object, whichever is in motion, will maintain what? It will maintain a constant distance from the fixed point. That becomes a circle. That is how in mathematics also, right? You will define a circle. You define how do you define circle in mathematics? You will say locus of all the points which are equidistant in a plane, because in 3D means it will become what? Sphere. So in a plane, locus of all the points equidistant from a fixed point. Okay, the fixed point will be called as the center of the circle, right? So if any object is going in a circular motion, we know that to change the direction of motion, because you know circular motion means direction of motion keeps changing. How do we know the direction of motion? It will be always along the tangent drawn to the circular. So to change the direction of motion, there should be an acceleration toward the center of the circle. That is what we call as centripetal acceleration. What is centripetal acceleration value? V square by r, where V is the speed or the velocity at that instant, and r is the radius of the circular path. Then the corresponding force, the force that is required is what? If you are looking to get an acceleration of V square by r, what is the corresponding force requirement? Mv square by r, where m is the mass of the object. Because if you want to have an acceleration A, means what is the required force to be acting? Ma, right? So this force should be provided by some external entity. Like if you look at a stone, we'll tie a stone to a rope and we'll start rotating the stone in a circular path. What happens if you look at that, right? The stone is here, a rope is here. Rope will exert what? Tension. So when I try to rotate the stone by tying it to a rope, rope will exert tension. You can see the tension force will be always acting towards center. So that will provide the centripetal acceleration. Like in friction case also we talked about it, right? When you are taking a turn on a horizontal road, circular turn, we will require centripetal acceleration. That is provided by what? Friction. We can even create banking on the road, where we will be able to use the component of the normal reaction also, okay, to support the centripetal acceleration. So like this we have already got some understanding about the circular motion. But here particularly what we are going to look at is the vertical circular motion of a part. Means what? You can again take the same example, like a stone tied to a rope, but you are now rotating in the vertical circular motion. How it is going to be? Look at this. So you can have an object, as you can see here, right? You can think of it like what? A vertical circular motion. Okay, so this is like a vertical circular motion. The object is going in the vertical circular motion. How it will be different from the normal circular motion, we will be able to see. In case of vertical circular motion, right, since you look at the motion of the object, as the object is moving in the circle, there is going to be a vertical displacement. Now whenever there is a vertical displacement, right, what is going to happen? Here we are going to talk about the impact of the gravitational force. Means, because we are trying to study the impact of the gravitational force by using what? Potential energy, right? The gravitational potential energy the gravitational potential energy, right, will undergo a change. Not just that, when you look at the actual vertical circular motion of an object, we will see that as it is going up, as the object is going up, it will slow down. As it is coming down, it will speed up. We will see what is the reason for that also. Means as it is going up, right, the velocity value must be decreasing. As it is coming down, the velocity value must be increasing. We will see what is the reason. What about the gravitational potential energy? Obviously, when you are going up means potential energy will increase. When you are coming down means potential energy will be decreasing. So we see that in case of the vertical circular motion, right, we observe that the velocity of the object in the circular path will keep changing. Then comes the question, can we call it as a uniform circular motion? Because remember, when we can say a circular motion is uniform, when the speed or the magnitude of the velocity remains same throughout the circle, then you can call it as uniform circular motion. But here you cannot call it as uniform circular motion. Why? Because the velocity magnitude will be changing. During the circular motion, the velocity magnitude will be changing. So vertical circular motion is not going to be a example for the uniform circular motion. Why? Because we'll observe that. So here I'm just telling you what we'll observe, but later we will even derive these results. Since the velocity magnitude is going to change, this cannot be taken as an example for the uniform circular motion. Remember, what is uniform circular motion? The speed value or the velocity magnitude remains the same. That is the uniform circular motion. So vertical circular motion cannot be the example for the uniform circular motion. This is the important one. And we'll see that the gravitational potential energy of the object in the circular motion changes, and the kinetic energy of the object in the circular motion also will be changing. But here, since we are in the work energy theorem discussion, right, let us see what happens with regard to the work energy theorem. So as you can see in the heading itself, right, what are we saying? Conservation of mechanical energy in the vertical circle. So which means we are saying that the conservation of mechanical energy principle will be applicable here. How? We have to see. Let us look at it. Okay, so we have an object which is moving in vertical circular motion. So the object is this is the center C. This is the object. Okay, so the object is moving in what? The vertical circular motion. Now the thing is, when you look at what are the forces acting on the object, so typically you will tie the object to a rope or something. You will tie the object to a rope. So where there will be tension that will be acting into the rope. Okay, and that will be pointing towards the center of the circle. Other than this, what will be the other forces? There will be, of course, the gravity part. But gravity is already accounted. Where is it accounted? In the potential energy term. Gravity is already accounted in the potential energy term. Here, just like we do in our normal kinematics problems, right, we will neglect the air resistance. We will neglect the air resistance. We will not consider the air resistance. Okay. Now, other than gravity, which is already accounted in the potential energy term, there is only one force, which is tension. Look at this now. As the object is going in the vertical circular motion, take any time, small displacement, ds. How it is going to be? The small displacement will be along the tangential path. What about the tension force? Towards the center of the circle. We call it as what? We can call it as a radial. What is the angle between them? At any time you take small displacement means the direction of the tension force will be radial. What will be the angle between them? 90. Which means the small work done by the tension force is what? T into ds into cos 90. What is cos 90? Which means not just the small path here. You take anywhere, like you take a small path here. There the tension will be again radial. You go here. Tension will be because you are tying the rope to the center, right? So when you are rotating, it means always the tension will be acting towards the center of the circle. You see here, what is it? Angle 90. So in the entire circular motion, work done by tension is going to be what? 0. Why? Because always the angle between the tension force and the displacement will be always what? If you look at any time, small displacement will be always along the tangential direction. So the angle between the small displacements and the tension force is what? 90. That is why whenever you look at any small time interval, work done is what? 0. If you add up all the small time intervals, then also the total work done is what? 0. So work done by the tension force in the vertical circular motion is what? 0, which means what are we having? Work done by, because there are no other non-conservative forces. So straight away we are having the result, work done by the non-conservative forces and other external forces is what? 0. That is the result, which means what? Which means, remember the work energy theorem concept, what is it? Work done by the non-conservative forces and other external forces, that is equal to what? Change in potential energy plus change in kinetic energy. We can write it like other way also. Change in kinetic plus change in potential. It does not matter. This is 0, right? Means 0 is equal to change in potential energy plus change in kinetic energy. This is what our conservation of mechanical energy, right? From here, what do we get? K initial plus P initial is equal to what? Ke final plus Pe final. Now when we say initial and final means, generally when you apply this conservation of mechanical energy, right, we'll have to choose 2 points. One of the point we call as the initial point, other point we call as what? Final point. But remember, you take any 2 points in the circular path. You take any 2 points. Okay. So initial point does not mean that it has to be always maybe a point at the bottom of the circle, because most of the cases, right, we will consider the point which is at the bottom of the circle as the initial point. But the conservation of mechanical energy can be used for any 2 points you choose. Like randomly you can choose 2 points on the circular path. You randomly choose 2 points. Maybe I'll choose a point here, call it as point 1. I'll choose another point. Same thing, kinetic energy at point 1 plus potential energy at point 1 will be equal to what? Kinetic energy at point 2 plus potential energy at point 2. Any 2 points you choose on the circular path, this conservation of mechanical energy will be satisfied. Okay. So this is a very important result in understanding the vertical circular motion. Okay. Now we will go into one of the important segments, that is the velocity relations. So velocity relations, right, they will be coming from straight away conservation of mechanical energy. Where they will come from? Where the velocity relations are going to come from? They will come from the conservation of mechanical energy. How it is, we will just see. So for this, right, like I said, we will consider, this is a very important point, the bottommost point. Generally we will take the velocity here to be u. The bottommost point, we will consider the velocity to be what? U. And as the object is going along the circular path, so how it will go along the circular path? It will go like this. You will reach a stage here where the rope becomes what? Horizontal. The rope becomes what? Horizontal. So this is, horizontal point. This is another important point. We will take it as what? Point 1. So point 1 is what? Where the rope is becoming horizontal. Let us call the velocity here is what? V1. What is the velocity here? We are calling it as V1. So we will try to find what is the V1 in terms of U. So what is the thing? U is general symbol that we use for representing what? The velocity at the bottom. Okay. The horizontal part, generally we will take it as 1, and there the velocity will represent as what? V1. So how we will relate the velocity? C. What is it that we have? Conservation of mechanical energy principle, right? Means what? Initially we will first close the reference, because always when you look at the circular motion, right, vertical circle, bottommost point will be the reference. It's like the reference that we can choose, because any other point will be above the reference only. So bottommost point is going to be chosen as the reference for the gravitational potential energy. Means P initial is going to be what? 0. K initial is what? Half m u square. P final. See this point, horizontal point, means what is the vertical height? Look at what is the vertical height. Vertical height is nothing but the radius of the circle. Whatever is the r is what? Radius of the circle, right? That will be the vertical height gained from the reference line. Means potential energy will be what? M into G into R. What is the potential energy? M into G into R. And kinetic energy will be what? Half m v1 square. What is the conservation of mechanical energy telling us? Initially whatever is the kinetic energy plus potential energy, which is what? Just we'll have half m u square, is equal to finally kinetic energy plus potential energy, half m v1 square plus mgr. We can cancel m on both sides, multiply with 2, we'll get what? U square is equal to v1 square plus 2gr. So clearly we can see one thing, u will be more than v1, because what is u square? U square is what? v1 square plus 2gr. U square is what? v1 square plus 2gr. Remember what we said? As the object is going up, the velocity decreases. That's what we said, right? Look at this, v1 will be less than u. v1 value will be less than u. So v1 is what? The velocity at the point where the object becomes what? Horizontal position. The rope becomes what? Horizontal. This is a very, prominent point in the entire vertical circular motion. This is the prominent point. First what we are going to do is, we will look at the prominent points, the velocity relations. Then we will look at the general point, because most of the times, right, we may get questions asked about the general point, but before that we should have understanding of the prominent points. So what is the relation we have? You can just take a note of it. What is it? U square is equal to what? v1 square plus 2gr. This we need to keep. So we are done with this story of point 1, which is when the rope is becoming horizontal. Now if the circular motion is continuing, so later we will also discuss about what will be the conditions for the circular motion to continue. So we'll talk about that in detail. But let us say the particle is going in circular motion. It will go to the topmost point. Generally we will call it as point 2. The velocity there we will take it as what? v2. Look at this again. We are initial. K is what? Half m u square. P is what? 0. The initial is our reference. Ke2 will be half m the v2 square. The velocity at point 2 we will take it as what? v2. P at the point 2, right? Look at this. Already one r and another r. What is the height of the point 2 above the reference line? Total diameter, right? R plus r, 2r will come. So mg into 2r, that is the potential energy at the point 2. So again same thing, half m u square, that is the total initial kinetic energy plus potential energy, that is equal to what? Half m v2 square plus 2 mgr. In this m is cancelled, then we will multiply with 2 on both sides. We will get u square is equal to v2 square plus 4gr. So what is u square? It is what? v2 square plus 4gr. You can see the relation. When you try to compare this with the relation of v1, right? You try to compare this with the relation of v1. What is the relation we have in case of v1? What is the relation we have in case of v1? U square is equal to what? v1 square plus 2gr. That is the relation, right? So you can clearly see that the relation in terms of the velocities will be what? U will be more than V1 will be more than V2. So as the particle is going up, the potential energy will increase at the expense of the kinetic energy, because total mechanical energy is constant, right? So we can even tell one thing, where in the vertical circular motion, right, where the kinetic energy is going to be least minimum, kinetic energy minimum means velocity minimum. Where the velocity is going to be minimum, velocity will be minimum at the topmost point. Why? Because topmost point, potential energy maximum, right? We are saying conservation of mechanical energy means what? When the potential energy maximum, kinetic energy has to be minimum. Okay, so this is about the discussion of the velocity relations for prominent points. Prominent point means one we taken when the rope becomes horizontal, other we have taken when the object is reaching the topmost point. Okay, then in the next session, right, we will look at the tension, how the tension in the rope is going to change as the particle is moving in the vertical circle, how the tension is going to change, that we will look at. And then we will also study the general position of the object. So in a circular motion we look at general position, and then we'll talk about the conditions. Like I said, right, we'll talk about some conditions for the particle to continue the circular path, like that. We'll talk about some conditions on the circular path to happen, or whether the circular path will happen or it will not happen. Okay, so the conditions about the object moving in the circular path we'll be able to discuss. So with that, the vertical circular motion will be getting completed. Okay, so we'll talk about the tension, how the tension is going to vary, and the discussion about the general point and the conditions for the vertical circular motion. These things we'll try to cover in the next session. Okay, we'll see in the next session.